All right, our final video on logistical growth is going to be logistical growth and limits. And there's really not a comprehensive procedure or anything like that to go through, and probably not going to go through every type of example that you might run into. What I'm going to alert you to are details and things to notice and incorporate into your thinking so that you can roll with pretty much any limit question you get related to logistical growth. And I'm going to use an old population graph that we had from a previous video and the graph of its growth rate. And as you'll see as we go through this, I was a little casual when I graphed those because the exact details didn't matter. But some of that casualness is going to come into play here and could lead to a misleading answer if you're not careful with your thought process. So in this case, I've instituted a population limit of 800. And we haven't talked about this, but the population has to start at a certain value. So in this case, we'll say it's a value of 100. In the classic example of a disease spreading through a population, you probably didn't notice the disease spreading through a population when it was small, when there was 10 cases or 15 cases. So maybe by the time you got to 100 cases, you think of that as times 0, and from there we're going to study the situation. So let's start with this very first question. The limit as t approaches infinity of dp dt. If I had to convert that into English, I would say, hey, what's the growth rate closing in on as I head out to infinity? Well, I can think of that in a couple of different ways, but probably the easiest way is just to look at this graph. As I head out to infinity, the growth rate is leveling off. In theory, it's still slightly positive, but it's getting more and more towards a horizontal tangent, which is a bad use of that term. It's getting more close to that horizontal asymptote is a better way to say it. So just logically, as I approach infinity, dp dt is closing in on 0. My growth rate is closing in on 0. Now there's a little problem. If I wanted to think about that limit, not in this form, but in the form of the equation, because it says limit as t approaches infinity of the dp dt, the growth rate, hey, I have that equation. Wait a second. As t approaches infinity, there's no t in there. Okay, so I'd have to do a little bit of a surrogate type of thinking. As t approaches infinity, the population would be closing in on 800. So that means my p is closing in on 800, which would make this end up, if I did kind of a intuitive thinking type of deal, this thing's closing in on 0.2 times almost 800, so it's closing in on about 160. But this thing, as p gets closer and closer to 800, is getting closer and closer to 0. So I have 160-ish times a 0-ish, which leads to a dp dt of 0. It's limit thinking either via equation or via graph, but there's a little bit of trickiness there. So now we're going to look at the next question, which is the limit as t approaches infinity of p of t. So I get to go ahead and look at the p of t graph again. And as t approaches infinity, if I'm not careful, I might just use a knee-jerk reaction and answer 0 because I'm thinking my growth rate is closing in on 0, but be very careful. This is asking for p of t. What is the population limit as t approaches infinity? So that would end up being 800. Not deep thinking there, but I'm just showing you how if you don't pay attention to all the little details, you're going to make a mistake. Let's look at a couple more. As t approaches 0 from the right, because you can't approach 0 from the left realistically, as t approaches 0 from the right, what is my growth rate? So this is a good one to think about because your instinct is going to be to write a 0. Because we've always casually drawn these graphs, you kind of assume that this slope and this slope is always going to match up. But that's not always the case. So as t approaches 0 from the right, what is my growth rate? And here's the dilemma. My instinct is to say 0 because the graph looks like 0, but as t approaches 0, my population is closing in on 100, and this dp/dt graph depends on the population. So I can actually just do some version of a plug-in, or I can do some kind of intelligent t-chart thinking. So you see my work down below. ST was approaching 0 from the right. My population was approaching 100. And when I plug that in, I get a 140. So my true answer for this problem is 140, which reveals that I really was casual when I made these graphs, because technically speaking, right around there I have a slope of 140. Right around there I have a slope of 0. And if I were to do the growth rate, it would actually start out at a value of 140, and it would end at a value close to 0. So just be careful, because it's easy to be casual with the graphs, but once you start doing limit problems, you have to be very precise with your details. All right, let's take a look at one more, and actually this is going to be the exact same question as this, just with different moving parts. T approaches 0 from the right is the same as P approaches 100 from the right. So I'm going to end up with the exact same answer. Seemingly different looking questions, same answer, same thought process. So we've certainly not covered all the types of limit questions you could be asked, but basically I wanted to let you know that in a lot of limit problems you can go by kind of intuition, by thinking about the graphs, but you should also go into every limit problem skeptically, because maybe your graph is too casual and you need to rely on the preciseness of the equation. And also go into every limit problem like a lawyer, read the fine print, make sure you know exactly what you're talking about. What sort of graph are you talking about? What sort of variable is being used? Enjoy!